Yeah, so this will be about the FHE landscape in Web3. I'm Miha Stopar. I was born at Ethereum Foundation. Yeah, so let's start. Um, so let's first have a look at what FHE systems are actually in production today. And there are three on this slide. And actually, if you will go and search for it, you probably won't find much more than these three. So the first one is Microsoft Edge password checkup, where FHE is used to compare users' password privately against a database of known compromised passwords. So the user's password is encrypted, and the service can see the password. But still it can compare it against compromised passwords. Then the second use case is Apple Live Caller ID Utah, where FHE is used to send to encrypt query to a server, a query about some particular phone number. So the server doesn't actually know the phone number, but it can still return us some information about this specific phone number. So this is kind of a private information retrieval. And the third case is Apple Enhanced Visual Search, um, which allows the user to search their photo library for specific locations. So, for example, whether there is an Eiffel Tower on the photo, but without actually letting the server know what they are asking for. Um, okay, no. Yeah, but these are all use cases in FHE use cases in Web2. But Web2 is actually quite simple compared to Web3 for FHE. Because, I mean, for anyone. Because in Web2, in cloud use cases, as on the previous cloud side, FHE actually protects users from a single service provider, and computation happens on a single server or perhaps in a single data center, and only the user holds the secret key. While in Web3, there are many parties that are contributing encrypted inputs. There are many entities that verify outputs, and nobody fully trusts each other because otherwise we don't have a decentralization of person. So there are quite some problems if you want to deploy FHE on chain. Uh, because one reason is the simply the size of ciphertexts. Because FHE ciphertexts are huge. We are talking about hundreds of kilobytes. So this is the increased costs. Then also there's a problem with latency because uh, the FHE that we know today is designed in a way that an error is inherent part of it. So when you encrypt something, you also put some noise to some error to the ciphertext. And if you multiply two ciphertexts, then also these two errors, these two noises, are multiplied and gets much bigger. But if the noise gets too big, then the decryption will actually return the wrong result. So so you need to, after a couple of operations, or maybe after each operation, with in the case of, for example, you need to do something that is called boot static, which is something that reduces the error in the ciphertext, so that the decryption still works correctly. But this is very slow, and it is, it hinders performance a lot. And also, there's a problem with storage, of course. It goes on the chain size. So for these reasons, the current FHE deployments in Web3 are actually hybrid architectures. So some part of it is actually completely on-chain, while the head computation is actually done on some special computers, which are called coprocessors, and usually run on accelerated hardware. And then to have some kind of verification, there's a component which checks whether these coprocessors already done the same way now. The second problem is trust and key distribution. So in centralized settings, like on the first slide, the user holds the secret key and the server only sees ciphertexts. In the centralized networks, there's a question who holds the key. If only the user does, then there's no multi-party interactions. And if multiple nodes hold shares, there's something, you need some kind of threshold encryption usually. So, you need a group of entities which hold, key shares, and then, this group or a subgroup of this group, collaborate together to provide the encryption. But as you can imagine, this brings uh, performance issues and also trust issues. And the third problem is programmability and composability. Because Web3 contracts are composable, which means contracts, smart contracts call other smart contracts. And in FHE world, that would mean each smart contract is a separate FHE circuit. But the problem is that FHE circuits are of different sets, so you might have different number of operations in the circuit. So these circuits might require different parameters. So it's kind of difficult to achieve the compatibility. But still, despite all these problems, I actually think that Web3 space, the ecosystem is somewhat is the space where FHCT can really come to life. Because, for example, in Web2, deploying the best crypto is very difficult because there are long release cycles, there's low tolerance for performance degradation, there are proprietary steps, while Web3 is much bigger. So developers are comfortable with zero-risk proofs, multi-party computation, commitments, entities, polynomial, interpretable proofs, and so on. Also, the ecosystem experiments rapidly, and everything is open source, and users expect recovery to be part of the step. Also, protocol updates are frequent and community driven. And actually, I think Web3 is the only mainstream environment where the distinct to public primitive is normal. Um, oh, wait. Yeah. Uh, no. Yeah. So, indeed, I think there is quite of a FHE momentum in Web3 right now. So, for example, for confidential compute layers, we have Phoenix, we have Clay, Pinko. Then for FHE runtimes and compilers, we have Zama, Sunspring, Phantom Zone, and for fairness and MDV, resistance with the Shadow networks, and actually many others. And there is a good reason for this because there are a lot of use cases for FHE in blockchain. So, for example, private stablecoins, where if you use FHE, then users can mint, hold, and transfer stablecoins without their balances or transaction history being publicly visible on Ethereum. Then confidential lending and borrowing, where users can deposit collateral and take loans, but neither the loan size nor the collateral amount is visible to the public blockchain. Then private automated market makers, where liquidity providers can contribute to pools and traders can swap assets without revealing pool sizes, trade volumes, or liquidates to the public. Then the fourth one is selective voting, where DAOs can conduct elections and votes without revealing individual preferences, while still proving correctness of values. And lastly, FHE EVM, which would mean a fully encrypted execution environment where smart contracts operate on inside the system. And there is another class of use cases which are perhaps more suitable for L2, more related to machine learning. So you can cluster user behavior. You can categorize transaction flows on 50 data, or you can predict the gas price spikes or liquidity demand. But it needs to be noted that the arithmetic for these use cases is actually pretty much different or from the one that is needed for the use cases in the previous slide. So, for example, for private stablecoins, you need exact arithmetic. So, if you do the comparison, it needs to be exact. There is no room for error. So, for example, if you need to compare whether I need to check whether A is has enough balance to do some necessary to vote. There's no room there's no tolerance for error. While in these cases which are more related to machine learning, there is a room for error and other skills might be used, other method which is more approximate by nature. Um, and there is some tolerance to numerical error. Yeah, and speaking about machine learning, in the last month or maybe in the last year, there's a lot of talk actually about blockchain and AI and machine learning. So, for example, whether Ethereum could be affiliated to ensure that the orders are executed correctly, because in this way, yeah, you could be sure that the model was do correctly, and also that also it might prevent having AI models just in the hands of you, for example. And the use cases could be, for example, finance, where investors can run risk models or portfolio analysis on sensitive financial data without revealing their positions to brokers or service providers. Then auditable financial predictions, where regulators and auditors can check the AI models for trading, risk scoring, or credit decisions were executed correctly without revealing meaningful data. And also collaborative trade, where multiple organizations jointly plan and one data with governance rules enforced on them. So, so we could see that there are two classes of use cases, and not surprisingly, there are also two classes of FHE schemes actually. So, integer FHE schemes, which are, for example, PFHE, fuel, BGD, BFD, and another class which is approximate FHE, for example, CKAS and these variants. So integer FHE is more suitable for exact computation for bitwise and integer arithmetic. It's more suitable for A1 state transitions. And also, the bit step is done after every operation. So if you remember, what I was showing, smart contracts being big smart contract being separate FHE received, and mentioning the terminal to the PDFP, that's not such a problem for the integer FHE because of these bootstrapping after its operation. While approximate FHE was things enable machine learning use cases because they compute on real and context numbers. And there are a lot of advantages of these techniques because you can parallelize them well, so doing a lot of operations at the same time. What's perhaps a bit surprising is that you actually can do also scheme switching. So you can switch from one scheme to the other. So for example, if you need to do a comparison of two numbers, which is by the way not trivial in everything, comparing whether two repeated numbers are the same. So if you have these two numbers encrypted by CKAS, then you can do scheme switching to, for example, PFHE, and you can do comparison there because comparison there is actually more efficient than for CKAS. And then at the end, you can again do this scheme switching. So in a way, you can have the best of both worlds. Um, yeah, so despite all these good things about FHE and Web3, so a lot of players, a lot of use cases, a lot of schemes, there are big problems, of course. And one was already mentioned, so it's key management. So it's best called FHE decryption, where parties need to collaborate to decrypt the result. Also, there is a correctness. So, because of this error, this is an inherent part of the jurisdiction. There's always this slight possibility that the jurisdiction will fail. But, and for example, for some cases, the probability of error can be set to, for example, 2 to the power of 42. But for Web3, this is not sufficient. You need to add error probability is something like 2 to the power 128, just because of the nature of the system, because of the sheer number of the operations. If an attacker could observe a lot of operations or even try to consider the ciphertext where the error will be very close to the margin. That would mean this probability of something goes wrong in the diction, and then observing these kind of operations, the attacker might gain some information about hidden buyers or something like this. And also the third problem is verifiability. So Web3 requires public verifiability. The validators must check correctness independently, but that's hard if FHE is used. So for example, I mentioned at the beginning, there are these co-processors which actually do the heavy work, and then you have a component that checks the results from these co-processors, but of course this is not the decentralization. So yeah, there's still a lot of issues I think for FHE to really lead in real systems. So I was thinking, what are the things that perhaps we can learn from zero knowledge proofs to speed up the adoption of FHE? Because the zero knowledge proofs are really the best thinking in Web3. The progress of the research of zero knowledge proofs has been really remarkable. But what's even more impressive is actually the speed of adoption in Web3 of zero knowledge proofs. I think there may be no other industry actually where research advances are adopted so quickly as zero knowledge proofs are in Web3. Just think of, for example, Brew 16 and Chrome. So these two research papers on the left side. So these are really household names, and everyone everyone in Web3 talks about Brew 16, for example. Of course, we need to change these household names because of quantum computers, but that's another story. So why did zero knowledge proofs evolve so fast? So I think there are three main points to say. One thing is the shift that happened to general purpose proofs, then having blockchain as a deploying layer, and the fighter of Web3. And if we look at each of these points a bit more in the details, so for example, the shift to general purpose proofs. So for example, at the beginning, we only have zero knowledge proofs for something very special. So we could prove in zero knowledge that some number is a square in something. But then later with Block 16, Block, and then Descendants, we actually got general purpose proof systems. And these unlock really a lot of use cases like rollups, GK layers, and things like this. And if you look at FHE, do we need the shift to general purpose FHE? I would say no. We already have what is needed. So we have integer FHE, we have approximate FHE schemes, and we even have scheme switching. So there are tools for some general configuration. That's not a problem. And the second point, having the blockchain as a deployment layer. So with blockchain, suddenly there was a new aspect where new cryptographic ideas could be deployed almost immediately. And this created an ecosystem where fast prototypes and libraries emerged almost overnight and are still emerging. And also, what's very important is that snarks, so zero-knowledge groups, turned out to be a perfect match for blockchain because they are short and can be checked quickly on chain. While for FHE, well, one hand it's similar, of course. We have a natural development happening with blockchain. We have a live adversarial environment that forces real engineering and new research is happening in public. However, there is a difference because FHE is not a perfect magical blockchain just because of, for example, of the size of the cyberdesks. And I think what was also very important for the adoption of zero knowledge books in Web3 was also the culture and the openness. So just as an anecdote, like 5 years ago, when I was working on ZKEVM at the Ethereum Foundation, I was surprised by how openly we collaborated with the external companies like Strom and Ukraine. I mean, of course, the common goal was still could be the robust layer 2 solution for Ethereum. But in most industries, you would expect competition and secrecy, not engineers from different organizations openly exchanging ideas and devaluing each other's code, as it was the case for us. Um, yeah, so and it's not only about collaboration, it's also about the libraries. That there's a tons of libraries for several rules like Leap, Snark, Benmar, Markwork, Schedule, Cool, Plotly, Free. And what's really important is that all these libraries are actually licensed under permissive licenses, MIT about you too. At the Zero Knowledge podcast, we take and like a list of common uh, bugs or zero knowledge code systems on this zero expert side. So there's really a lot of collaboration and openness. While I think that's actually slightly different for NKT, there's a bit less openness there. Um, yeah, so what could be potential paths forward to speed up the adoption of FHE? So I think one issue is this about designing sustainable economic models because still the FHE introduces a lot of overhead and also the heavy computation is actually done on accelerated hardware, which is expensive. Then the second thing is advancing verifiable everything so that we have a proof that things were computed correctly to have a very decentralized graph. Then there is exploring decentralized key management models like multi-key models. And also I think it's important to have a kind of open benchmarks for developers to know which things are most suitable for which use cases, what's the overhead of skin switching and things like this. So yeah, if you want to have a look, there's a kind of long write up about these topics on your research. You can find it on this link. Yeah, that will be all from my side. And yeah.
Thank you, Miha. Maybe a round of applause for Miha. Are there any questions in the audience? Let me have a look. Someone wants to know something more from Miha, or we have one question, I see. Let me also change the you see. Sorry, just yeah.
Just for clarification, one of the early slides you were talking about coprocessors, we're talking about GPU farms and such. These are all proprietary systems, right? It's run by an independent company for profit, proprietary, correct?
You mean how do you mean by no for project?
All of the slides I've seen so far, and you mentioned one towards the beginning, that it was too computationally expensive to do this on chain. And therefore, there had to be, for practical purposes, an offloading of the hard work to something else. And you gave examples of what you called a coprocessor. And in another slide, you said GPU farms. So I'm kind of putting those together. Are you suggesting that there is no way currently for this kind of solution to be built other than by offloading to an independent, not on-chain proprietary coprocessing or GPU farm? Question.
Yeah, I think it would be very difficult to do this without it.
So if this business is in business today and then in 12 months it's out of business for whatever financial or economic reason, what do we do?
Oh, I have also, I don't know if I have answer this, but it's actually one of the points that I exposed on the last slide. So building sustainable economic models. I think that's still kind of an open question. Maybe Phoenix might have better answer to it because they are more they're deploying things.
Yeah, maybe I can say something to that. We have, after this presentation, we will actually have a look at Phoenix that Lauren, who is listening in, can maybe as well address this question. I think, because then we look at one of the co-processors, basically. And one more question, yeah?
Just from your general experience, were there like attempts of commercial adoption of FHE in biotech? And if they failed or were cancelled, or like people were not just didn't dare to do that, like what do you think, what are the practical obstacles?
So I think still I might be wrong, and maybe things changed in the last 6 months a bit when I was working on other stuff, not FHE. But my impression is that it's there's FHE unit has a lot of quite significant overhead of computation, and also these have implications on performance. So it's still very difficult to actually to deploy something in production and to make it profitable. Also, on the other hand, there are zero-knowledge proofs, which actually a lot of problems you can solve with zero-knowledge proofs alone. And I still think that actually, in most cases now, people still try to solve things with zero-knowledge proofs, or maybe multi-party computation, because it's just more efficient at the moment. Whether this will change or not, I don't know.
And let me check in the audience if there's any more question for Miha, or if we keep it like this. I think, Miha, this was it for now. Thank you so much for your presentation.
Thank you. Bye-bye.
Bye-bye.